Let's start with a little mindfulness wake up here. All right, sitting up. Pull away from the back of your chair for just a minute, supporting yourself with the strength of your back, letting your shoulders fall down and back. Notice if you're holding any tension in your face, maybe an expression. Maybe you're clenching your teeth. See if you can soften any of that. Coming into our bodies, just noticing the sensations of sitting. Breath naturally ebbing and flowing, not trying to control anything. Turning your attention to the space behind your eyelids. Noticing that even with your eyes closed, you still see. Looking out into that shimmering darkness. Where's the edge of that darkness? Letting unfold what just naturally unfolds in that space. It might be more shimmering, might be figures, colors, might not be much. Just let that be and notice it. Let's start some calculus. Okay, did everybody get the email about skills checks? Yeah. Is that good? That's good. I was reminded by a friend who was visiting me that I had promised, who was reminded by another friend perhaps, that I'd promised no skill checks on Mondays because that would be evil. So, I'm sorry I even tried that bullshit. It won't be. We might start something new. We might start integration because we kind of need to get rolling on integrals in the multivariate sense. Today, and then, we'll talk more about the skill checks, but there's 4 new webworks up to practice. So I think those are partial derivative or chain rule. These will be the things. I think there'll be 4 of them. Chain rule, directional derivatives. You know, another guy I haven't seen in a while is Mr. Offman. Yeah. Directional derivatives. Optimization. What's that?
Have you ever seen Offman?
Have I ever seen Offman?
Yeah.
I've heard of Offman.
I've heard of him.
Optimization unconstrained. That's what we kind of did in my Monday online lecture, and then talked about more on Wednesday. And then Lagrange multipliers, which is what we're going to talk about today, which is actually constrained optimization. Multipliers, which is constrained optimization. Let's just get into it. Yeah, very cool stuff. I'm sorry, what was your name again, friend? Brianna. What's your math background?
Digging up to Calc 2.
Oh, awesome. So let's do some map work. We're out hiking around, and we just did a hike, and we looked back at our map app that keeps track of the hike. And the topo layout of the land looks something like this. So I'll get some actual lines on here soon. So that's our topo map. Yeah, and let's give some heights here. So this is at 200, 150, 100. So then this would also be 150, 200, and 50, and then 0, I guess, following suit. And then it's 100, that's 50, 0 feet high. So that's a map. What does it look like? I'm standing right here, looking that way. What do I see? Yeah. One hill?
No, sorry, that was like not a hand raise. That was like
Oh, okay.
showing you was my
So what do I see? Two hills straight ahead, right? It's kind of a valley, low valley. I could walk between here. Is everybody picturing that? Brianna, is working for you? Okay, awesome. But that's not the way I hiked, because I'm just a maniac. So I was just like, you know what? I'm a math guy. I'm hiking in a straight line. Honestly, I find myself optimizing my path pretty often in life. Just like sidewalk, schmidewalk. I'm walking across the grass because it's best and fastest route. And so my route looks like this. I'm headed in that direction. So the black path is how I actually hiked. What did my hike look like? So does anyone want to just tell me, like, sorry, yeah, what's going on?
So you started out at 0 and you went up a hill,
Yeah, going up the hill, and then what happens?
up
Down the hill. Well, is there a moment when I'm at a highest point?
the hill. At a highest point in that travel, yeah.
Yeah, where's that at?
59.
The 150 is my height, yeah. So notice that right here, and it seems kind of obvious in a way, especially with the stories Zara was telling us, right? That as I walk across here, I'm at 0 and I go up and I go up. But the thing that I want to point out is that this was the maximum height that we achieved. And it's the moment when my path is tangential to one of the level curves. So let's say, what if this level curve hadn't been like this? What if it had been like this instead? How does that change my max height? Because is my max height, it's not still here anymore, obviously, because I didn't walk it.
slightly higher.
It's a little higher, right? And it would be at the exact moment that I hit whatever level curve corresponds to the one that is tangential to that. That's where I'm going to hit my maximum. Any other level curve that's not tangential to my path means that my highest point isn't at that level. Does this make sense?
Tangential point is the highest point.
The tangential point is the highest one. And that's the idea behind what we're going to talk about today, which is the method of Lagrange multipliers. So, method of Lagrange multipliers. And we're going to have the basic multipliers. I'm having trouble with that word. So the problem is going to be this. Find the max min of a function of two variables. And here, the function of two variables looks like those mountains that are in front of me that I'm walking into. That's the z equals f of xy. It's that surface that makes the mountains up. And here we're just looking at the top-down view at the level curves. So we want to find the max min subject to such that, or whatever, some other function g of xy equals, now you'll see two versions of this. There might be a constant here, or there might be a 0 here. You could just put the constant into the function g. So this is called my constraint. And that corresponds to the black path over here. I was constrained to that line. Where, if I only can walk on that line, does the function that determines my height max or min out? And so this is actually called the objective function as well. Now, I was telling Alexander on the way over, I don't know enough physics to talk about this intelligently, but apparently in physics, there's two kinds of mechanics. There's Newtonian mechanics, which I actually understand something about. That's where you balance forces, make sure the horizontal forces are balanced, and you talk of vertical forces. And then there's Lagrangian mechanics. Does anybody know anything about that? What I heard is there's something like, you form this thing called the Lagrangian, which is the potential energy minus the, what do you call the other kind of? Kinetic, thank you. Kinetic energy. And then you work with this. And this quantity, apparently, I watched a little bit of a video, but not enough to understand this, that this quantity doesn't have any meaning unto itself, but it provides an amazing tool for doing this stuff. Has anybody ever done any of this here?
Maybe I have, I just don't remember.
There we go. So maybe so.
Our other physics guys are not here to help us.
Yeah.
The one time.
Yeah. Wonder where those guys are. I guess one of them's sick, right, Daniel? Should send me an email. So we actually have something similar here that we would look at. There's a thing called the Lagrangian, and it does have this beautiful L. The Lagrangian's equal to the objective function minus lambda times the constraint function. And we don't put the plus c on there at all. So we get something like this, and what I don't know right now is the connection between these two things. I'm gonna, maybe this weekend, I'll spend a little time digging in. What do you study, Marissa?
I study
Brianna, sorry.
Oh, no.
Study what?
biology.
Bio, okay, cool, so yeah, not your thing, okay. And here's kind of the insight we're gonna get here. So first off, what if I think about the gradient of this Lagrangian? So I'm talking about the gradient here. This is, so this is a function of two variables, so I've got the gradient, and so that's equal to the gradient of f at xy minus lambda times the gradient of g at xy. And essentially our problem comes down to the possible maxes and mins will occur as critical values of the Lagrangian. So in constrained optimization, let's see, so again, this is the Lagrangian. In constrained optimization, critical values in XY pairs occur where the gradient of the Lagrangian is equal to 0. Now what would that mean? Well, that means this, that the gradient of f at xy minus lambda gradient of g of xy, that equals 0. And let's write one more form of that. And I'm just copying down here. This was the gradient of the Lagrangian. That means that the gradient of f equals the lambda, some multiplier. This is called a multiplier. And it's a constant. It's an unknown constant. Is equal to lambda times the gradient of g. And so this is what we're going to start with. We're going to use this equation to get critical values. And then from there, we can kind of just grok our way to the answer. Take a look at that really quick. And I want to point out something here. So the green stuff here is my G. These green lines are the level curves of G. Of F. Thanks, yeah, good eyebrow furrow there. The black line is actually, if I'm looking down at it, the curve G of xy equals C in the plane. So let's think about the gradient. Now, green curve is the gradient. At this point, the gradient of F is pointing perpendicular to any tangent line that I might have there. So this would be gradient of F. Also, the gradient of this line is a perpendicular to that line. So the gradient of G, so let's see here. So here's G of xy, better label some stuff. And then the green this is F of xy level curves. This is the gradient of G. And what we decided was that when the constraint was tangent to a level curve, we had a maximum value at that level, what we kind of intuited. When the constraint is touching one of the level curves at just one point, their gradients will just be multiples of each other. Now let me show you what I mean in a slightly different example, because that straight line there is maybe a little misleading. Let's do multiple colors. So let's say that the blue equals level curves of f of xy, and we've got something like, do a little kidney bean action there, or something, pear, whatever. Let's do that. And then I'm gonna let red be my g of xy equals a constant. So let's say this curve goes something like this. So now, if I'm going to have an extreme value on this curve, it's going to happen only where the gradient of the blue curve, so like there's actually a couple spots here this might happen, but I just made this one really obvious. So the gradient of the blue curves is perpendicular to the tangent line at that point. The gradient of this red curve is also perpendicular to the tangent line at that point. So here, notice that we have gradient of G is equal to some positive multiple of the gradient of F, which is, I'll put that in blue. So the whole secret behind the method of Lagrange multipliers is we're going to figure out where the gradient of this thing is a multiple of the gradient of this, and that's the only place we could have a max or a min occur. Let's take a look at another spot, like look right here. So here, the blue curve, its gradient is pointing like that. The red curve has a gradient that kind of goes like that. Does that make sense, or do I need to explain that a little bit? Yeah, we're good? So notice that they're not multiples of each other. They're totally different directions. And it makes sense that I don't have a max or a min there, because look, on this red line I'm going, I didn't put high if this is low or high, but let's say this is low here and this is higher. I'm higher, dropping down, dropping down, dropping. Now I'm kind of, dropping down a little more. Now I'm kind of going back up. And as I pass across this way, if I were walking on that red line, I'd still be moving uphill here. Do you see that? That's the important thing to see. And that the only time I would actually have a potential max is when I've got this tangent here. So I'm going down, going down, going down, going down. Right at that moment, I start to go back up. So let's practice this. What time we got? Okay, we got good amounts of time. Also, I'm kind of thinking about creating a way to do some extra credit for anybody who might be interested. Make up a skill check, make up whatever. I guess that's all we got, is skill checks, right? But to make up some sort of skill check that maybe you didn't do for some reason or another, or you just kind of left in the dirt because you were like, fuck it, I'm not doing it anymore. You retired. So it's gonna be some problems that you can do. There'll be a lot more work than a skill check, but they're good. I own this, I control this way, and I can get these points back by doing some extra work. Anybody can do them too. They're actually kind of cool problem sets. So they were the ones, I don't know if you remember when I came in here the first day of class and I said, I totally took a part of this class out. That's the part of this class that I took out. So I was like thinking, let's put it in as extra credit if anybody wants to do it. It's too late to change the syllabus. little too late. So let's look at an example. And let me show you how this works, because it's a fun process. So we're gonna find the max min, sorry for the red pen, of f of xy equals x squared plus 4y squared minus 2xy plus x minus y. Very involved. If you looked at it, it kind of is an elliptical paraboloid. So it's like a thing like this, but it's tighter on one side and wider on another axis. And it's rotated in space, so it's not just sitting all pretty in the XY axis. It's just kind of floating in space, rotated a little bit. This is a rotation term, by the way. Subject to the constraint 3x minus y equals 6. So this is my f of xy, that's my objective. This is my constraint. And the first thing we're gonna do, so step one, I gotta get rid of this damn red pen. It tricked me with the blue cap. Blame the pen. So step one is find the gradient of your objective and the gradient of your constraint. So let's take a minute to do that. Do you do partial derivatives? Have you done partial derivatives? Okay. Is everybody okay on the lighting? Especially here. Yeah, I like it. I like it a lot. All right, good. Good. Let's make sure I want everybody to get here with me. Oh, man, it's so nice to not be sick. Being sick, just like you're like, why didn't I appreciate being healthy more when you're sick? Right? Isn't this like, oh, I'm such an asshole. Why don't I appreciate my health more? And then it comes back, and then you start doing stuff to make yourself feel terrible again. I miss being sick. I'm gonna have a beer. No, I'm not doing that. That's how I lost my fingertip. And a lot of money as a grad student.
Not as much as the crypto though, right?
No, it's not even close. At least I don't take out student loans for the crypto, like I did for the beer. So step 2 is we're going to set gradient of f equal to lambda gradient of g. And we're going to introduce that lambda. So in other words, I'll kind of walk us through this first one. I'm going to have 2x minus 2y plus 1, 8y minus 2x minus 1 equals lambda, scalar multiple of the gradient of the constraint, which is pretty sweet here for sure. And now we're going to take the equations we get out of this. We actually get 2 new equations out of this thing. Right? Does that make sense? You still cracking up at
Yeah, sorry.
my honesty? I shouldn't say it. I guess I shouldn't tell about what a degenerate I'm doing. So the x component must be this x component. The y component must be this y component. So in other words, 2x minus 2y plus 1 must equal lambda times 3. So I'll just write 3 lambda. Stop. So I'm saying that for these 2 vectors to be equal, that this has to equal the first component here, but it's multiplied by lambda. So 3 lambda.
Oh, you're just showing us first component.
Yes, sir.
Okay.
Yes, yeah. So I'm just going to pull apart the equation. So maybe I'll put that up here. Pull apart into, I would say 2, but we might have a 3-dimensional one, into separate equations. And so then go ahead and just, I'm not going to say it out loud, just get that second equation. And then, look up. Cool. Let's give everybody a chance to catch up. Or just keep being a maniac for cranking on it. That's good tea. The other thing, I spent way too much money. Did I tell you how much I spent on tea?
$300.
$300 on
I think
tea
you
this
spend
year.
more.
I think I'm going to spend more. I'm going to spend more. Tea doesn't let me down like crypto does. Okay, so everybody cool on these equations? Awesome. So now I've got 2 equations in 3 unknowns. What's another thing I know about x and y? What's another equation that I actually already have? The constraint, yeah? This guy right here. So what happens is from this process here, you introduce this new lambda, which seems like it's going to be a pain, but it gets you these 2 new equations, but you still have that. Now you introduced an extra variable, but you're going to pay for that extra variable with a 3rd equation. And once we get that, everything is completely defined for a 3x3 system. So we've got 3x minus y equals 6. So toss in the constraint equation. And at this point, we've got 3 equations, 3 unknowns, and the unknowns, of course, are x, y, lambda. We're going to find all 3. The lambda has a very special interpretation, but let's just do it first and then talk about what the lambda means. Is any questions getting to here? Let me stop. Let me switch colors. You doing good, Czar?
Yeah.
Awesome. Eric, you good? Solid. Camila, you good?
Yep.
Awesome. All right. You all good, Christian?
Yep.
Cool. Just checking. Don't stop working. All right. So now I've got to solve this. Any suggestions? How do we start cracking this black ice?
You could
Plug it into the other one.
Yeah, like solve like the constraint for like
Yeah,
y
for
or
Y, and then
something.
plug in Y.
Could totally do. Yep. So let's kind of go through the ideas. I could solve this for y equals 3x minus 6.
You could also just like the 2x and negative 2x could line up and like that.
Those 2 would cancel kind of nice there. Yeah. Another thing I could do is multiply this equation by -3 and then it would be 3 lambda over here, and then set them equal. Do you see what I'm saying? There's lots of ways to go. So at this point, you know, your mathematical creativity can take hold. I think the route, let's call them 1, 2, and 3 so we can get a plan written down here that we can retrace if we needed to. I like the idea of adding equations 1 and 2 because the 2x and negative 2x will cancel. Does everybody see that? We're good? So so step 1 is equation 1 plus equation 2. Highly recommend you label your equations when you're doing this work for your own sanity, right? Like, how did I get that? Oh, I added 1 and 2. And I put a little colon. So let's all do that and catch back up in the middle. And it kind of ends up nice. Why don't you take it from here? Take a minute, just on your own, head off into the wild, set up camp, and we'll see how it goes. I'm gonna clean up the board. And we should all end up with the same answer no matter what. There is a unique answer. Filthy rag. Miss you. Oh. Did you have a question, Alexander?
Maybe.
Okay, yeah.
How do we end up at 3y equals lambda? I'm sure it's obvious, I just missed
So I'm sorry, what was your question?
3y equals lambda.
Yes, sir.
Where do we get that, where do we land on that?
How did I get that? I added equations 1 and 2.
Is 6y, oh, right.
So yeah,
No, I
6.
got that.
You're with me now. Awesome.
Sorry.
That's okay.
I knew
No
I was
sorries.
like, it was like right in front of my face.
No
It makes
sorries
sense.
needed in this class ever. We're all friends. And it's just math.
It's math.
It's just math.
It only answers everything.
But I'll be curious to see what different routes folks went. I thought that was Othman coming in.
He's a late man, but he, you know, at some point he's gotta call it. It's like, I missed
Did
it.
you call it, Othman? Oh, come back to us, my friend. Okay, so we do that. Let's see. This is my route. Well,
Is this supposed to work out nice, or is it gonna be kind of?
no, the numbers are hideous.
Okay.
Does that sound right? Okay, yeah. Is there a 31?
That's.
Okay, yeah. So good. 2x minus.
Math.
What's that?
Just one math one.
So now I got the equation. I'm gonna call that equation 4. Now, so. 2 and 4. Yeah, and we'll all get the same answer, and you'll know then whether you're, no, the constraint, what am I doing? 3 and 4. Because 3 is, yeah, otherwise I gotta do lambda across. 3 and 4. 3 is a nice equation. And then this is a new equation in just x and y. 2x minus 11
And this is not the only way, so don't worry about like trying to do what I did. I'm gonna make it up like that. So everything's kind of lined up. So this was 3, this was 4. So then I'm gonna take 11 times equation 3 gives me 33x minus 11y minus 66 equals 0. And then I'm going to subtract.
Disgusting
It just keeps getting worse too.
And then I'm going to take 4 minus 11 times 3. I take full credit. I made this problem up. As you can tell, it's not from a textbook. So then that's going to be 30. Oh wait, 4 minus. So 2x minus that is negative 30. There we go. I knew there was something like that. And then those cancel. And then that turns into positive 67. Anybody got a 67?
Yeah.
Yes? Guys got at least one. Yeah, we've got one. Yeah. Okay, we got multiple 67s. There's a 67 in this thing somehow. And I remember that, so here x is 67 31sts. And I think let me double check my old notes. You got? Yeah, you know, and it's probably just some small algebra error. It looks like I didn't feel like finishing it. But a couple folks have got this, right? The same x value. Is that Corvick? Did you get that? Yeah. And then now that once you got that, then just start plugging into it like any equation, get the other variable, and then you can work your way back to getting lambda. So I'm going to plug, oh wait, I heard people don't like that. Substitute. Substitute x equals 67 31st into the constraint, why not? And we're going to get 3 times 67 31st minus y equals 6. Move the y over, move the 6 over, so, oh God. It's 211? What's 67 times 3? 201. 201 31st minus 6 equals y. So y equals 201 minus 6 times 31. Oh, that's easy. That's 186 over 31. And then that's 15 31sts. Yeah? Oh yeah, hell yeah. Okay, I'll take it. I'll take anybody who got that, that's the right answer.
I just didn't want to do that last.
Yeah.
thing. I was like,
Yeah. I feel you. But then lambda's just 3 times y, right? So, and then lastly, since we know that lambda equals 3y, we have lambda equals 45 31st. Not bad. Not bad. 45. Worst things is you get all these same numbers. Anybody?
Yeah, once I reduced them.
Yeah. Oh, you had.
I was at like 495.
Good God. All right, so this problem's a little tricky. One thing I want you to note about this problem, our constraint was a line, right? Our constraint was this line that extended infinitely in both directions. Our constraint was unbounded. Does that word make sense when I say that in this context? Unbounded, couldn't fit it in some square. In real analysis, you know, same kind of idea, just here in 2D, was unbounded. So things are a bit tricky. We're gonna do one that's opposite that in just a second. Tricky in terms of, is this a max or a min? We have to kind of almost go to a graph at this point and analyze the situation. But remember what I said this thing looked like before? It was kind of some sort of elliptical paraboloid like this. And we were constraining ourselves to some line in the plane. So what does that look like on the surface? On the surface, if you restrict your x and y inputs to just that line, that 3x minus y equals 6, and traced it out, you would see something like this on the curve. So if this is the line, and I just plug in those xy pairs into f of xy, I would get just a parabola floating in space. So what do we got, max or min? Minimum. So what we found exactly was that point right there. Now, there are three things to report here. So now we don't care for our purposes about the multiplier. Let's get one last thing written up here. So we report our results. We have a minimum, and this is the part I should have worked out, of you kind of need to plug the x and y coordinates back into the original objective. What is it? Plug. Substitute. Substitute. Yes, I'm talking like some sort of low-class mathematician. So we plug those back into our f of xy. Let's see, and I got x was, what was my x? 67 31sts, and then 15 31st was the y. So this you would compute if you cared enough, but we don't. It's like just freaking horrible, right? Because we got to do this squared plus 4 times this squared. Oh, gross. No thanks. No thanks. Compute and get number. So we have a minimum of this output level at 67 31st, 15 31st. And you want to report the where and the what for any optimization problem. And of course the nature of it as well. Is it a max, a min, a saddle? We don't know. Okay, let's do one more. Because I want to do one where we do have a bounded constraint, because it's actually a lot easier here. I'm just going to say the phrase extreme value theorem from Calc 1, when you had find the max min of some function, but you had a closed interval. Do you vaguely remember this? Yeah, you had a closed interval, and so you looked at the value at the endpoints. You made a little list, values of heights at the endpoints, and then any critical value heights in between. Made a list. Tallest one was the max, least one was the min. So that's what this becomes when we have a bounded constraint. And there is a web work with, I think, 3 Lagrange multiplier problems. Don't do the first one first. I didn't have time to reorder them. I would start with 2 or 3 and then do number 1 last, because it's got X, Y, and Z in it. Same process, and if you want to talk about it on Monday, happy to do that. Maybe I'll just write up a solution so you can have that for your own enjoyment. New color, new example. Let's see, what do we got here? Oh, this looks happy. So find, that's not a new color, find the max min of f of xy equals 81 x squared plus y squared, subject to or such that 4x squared plus y squared equals 9. Here we go. Now we're cooking. So let's think. Always try to understand what you're solving, right? Like have a visual image, because otherwise you're just kind of floating in abstraction. And sometimes that intuition can be very, very helpful. Oh yeah, there we go. So this thing, this is another, if I sketched out z equals 81x squared plus y squared, it's another parabolic ellipsoid. So it's like this round thing, like a nose on a, I don't even know what it's like, a nose on a rocket, I guess, but it's not as pointy. Like, I don't know what the hell that looks like. It's round. It's an ellipse. If you take cross sections like this, they're ellipses. So just think of a bunch of ellipses stacked and they're getting bigger and it's all smooth. So that's what this thing looks like. What does this look like? Yeah, what were you drawing out there? You're right. An ellipse. Do we see that that's an ellipse? Awesome. So remember that an ellipse, we talked about this once. If you see an equation that looks like this, and sometimes it's not obvious that there are fractions there, but this equation is an ellipse centered at the origin with A as the x radius and B as the y radius. So in other words, it looks like this. Move out A units on the x from the origin, move up B units from the y, and it looks like that. Poorly drawn, but that's the idea. And so here, what I would do, if I wanted to understand this, I would divide both sides by 9. And then I would get this to be completely underneath the x squared. So that's actually x squared over 9/4 plus y squared over 9 equals 1. And then think about, what is this the square of? And here it's so pretty, right? This is x squared over 3/2 squared plus y squared over 3 squared equals 1. So that means my x-axis has a 3/2 radius, and my y has a 3 radius. And I can sketch this thing out really pretty nicely. So on the y-axis, I go 3. And the bigger of the axes on an ellipse are called the major axis. The smaller one's called the minor axis. And so that's just 1.5. And so that's what our constraint looks like. And it's bounded because it lives in some box. It doesn't shoot off to infinity. When we have a bounded constraint like this, so think about what might be happening here. So this thing's floating in space up here. Its vertex is actually right at the origin. So let's see. So this thing's kind of like that in space. And then we've got this ellipse down here. And let's see, so on the y-axis, it's a little longer, so it's kind of like that. Down below. And we're restricting our attention to only these x, y values down here. Yeah. Is it kind of making sense, the picture? Yeah. So when you look at those x, y values, you're going to have some kind of just shape traced out up here. And I kind of think it might look something like that. If you just restrict your attention to these input values on the ellipse, you would see this ellipse that's all bent and warped floating in space, kind of like that. But we'll find out if I'm right. So when we do this for a bounded constraint, if constraint is bounded, then find all solutions to the first order necessary conditions. In other words, these are first order necessary conditions for a max or a min. First order meaning first derivative. Necessary meaning that anything that is a max or a min must satisfy this, but not everything that satisfies this is our max or a min. And then substitute, if I can even spell that. Maybe it's I say plug because I can't spell substitute. Oh my God. Substitute each critical pair into f of x, y, the objective. Largest value equals max. Smallest value equals min. And I'm gonna write up here, think extreme value theorem from Calc 1. It's exactly the same process. So, pretty close to the same process anyway. Alrighty, friends, so let's do it for this problem. Hey, can you do me a favor? Let's get these two equations wrapped up. And then let's check in. We might run is it okay if we run a few minutes late today? If you gotta go, no? You gotta go?
I haven't advised meeting at 3:15.
Oh, not that late. Yeah, like just 5 more minutes.
Yeah.
Yeah, okay, all right.
All is well.
Okay. Not, yeah, I don't want to be here till 3:15 either. I just kind of want to make sure we get through this. And if we don't, we'll just call it. It's all good. Should I better write this stuff down? So. Bless you. Bless you again. Thank you. Are we identifying the F and the G properly just to make sure everybody's simpatico on that? All right. If that even makes sense, I'm not sure. So gradient of F. Gradient of G. Sanity checks along the way, and then convert that into the two equations using this relationship up here. I kind of love doing these. Seems super mystical. It's like you made the problem harder by introducing this new thing, new variable, but it actually makes it solvable. And the work just turns into, kind of lovely algebra. And I think we're gonna need to touch base once we get those equations up. We also have the constraint, so also we know that 4x squared plus y squared equals, 9? Yeah. Let me know. If there's any questions, any troubles. Good, Camilla. Sorry. How you feeling? Good? You're Dan now. You can be whatever you want, because there is no other Daniel.
No email.
Buddy. All right. Hope you're well, Daniel. Hope you're getting well. So now we gotta solve these things. Is there any obvious values that maybe solve the first two? Anything you could just tell? What do you think, Cormac?
I was thinking, what is it, gamma?
Yeah,
I was thinking gamma make it equal to 1.
but then we still, so if you set gamma equal to
I was talking
1,
about the second one.
oh, gamma equals, or lambda, you mean,
Lambda.
lambda equals to 1. Oh yeah, that's a nice one. Yeah, and then y could be anything.
Yeah.
Definitely. Yeah, that's a good one. Any even lower hanging fruit. Fruit that's been on the ground fermenting. It's alcoholic. It's Friday. We're gonna eat rotten fruit. Party down.
If you do lambda equals 8/162.
Ooh, you get too fancy. Let's think less fancy. What are the simplest numbers in the world?
2, 4.
2, 4 simpler. What's the simplest number in the world?
0.
0.
Lambda equals X.
Well, x equals 0. So now if x equals 0, notice this is 0 equals 0. If y equals 0, this is 0 equals 0. So those are definitely solutions that we have here. I'm going to show you how to rewrite this thing a little bit. There's probably some factoring you can do. I would put everything on one side because that's just like kind of how I was trained. Your mileage may vary on your training. Well, I hope it does, right? I hope that I've had a little more training. So I get everything to one side. I'm going to factor each side because that actually makes things a little easier to see what's going on. And then factor y out here, I factor 2y out here even, 1 minus lambda equals 0. And now we're seeing Cormac's lambda equals 1 more manifest more clearly, right? You've got a product, either this is 0 or this is 0. Either this is 0 or this is 0. So from this, I know that x equals 0 or 162 minus 8 lambda equals 0. And then here we get y equals 0 or lambda equals 1. So that was a good eye on that one, Cormac. Very nice. Notice we have 2 different multipliers now. So we have 2 different points. We expect 2 different points here. Let's see, I'll make sure I don't run us too late. I'll stop in just a few minutes here. Is there any questions on how I got to where I'm at? Okay, cool. So now we can come back over here. Let's go through the possibilities here. If lambda equals 1, let's just kind of start there. Let's separate our answers by the lambda values. Let's use those as little organizing blocks. If lambda equals 1, this equation's satisfied, and y can be anything. Do you see what I'm saying here? If lambda equals 1, y could be whatever I want, because it's 0 times y. So if lambda equals 1, let's just, y is free. And then if I put lambda equals 1 into this equation, let's call this 1, let's call this 2. And equation 1 becomes, this is where if you like working with equations, you're going to have a really good time. X times 162 minus 8 equals 0. What does that say? What is the solution there?
0.
X is 0, right? So this is some number, who cares? It's not 0. So that says x equals 0. So notice that if lambda equals 1, x must be 0. If x is 0, I got this guy here. Man, stuff's starting to unravel. Let's call this equation 3. And I think we can kind of end it. Maybe you could try to finish this up on your own over the weekend, and I'll create a solution. Because you're kind of rolling now. So you could think of this as your first practice problem. So subbing, that's a different way, subbing x equals 0 into 3, the constraint, we get y squared equals 9. So what's y? Plus minus 3. Plus minus 3. Remember how the shape looked like the edge of a Pringles? essentially. So lambda equals 1 is going to be, we're going to have these two, and this doesn't look good, but these two are at the same height and these two are at the same height. We're going to get 2 maxes and 2 mins. And here we're seeing that right now. So, therefore, 0, comma, plus or minus 3 are critical values. Now we got to find the other critical value. How do you think we're going to get the other critical value, and we'll call it? What do I need to do? Coming back to these guys. So we assumed lambda was 1. Now what do you think we want to assume?
Lambda equals 162/8.
Yeah, now let's make this one true and work from there. So here's your job, and try to finish this up. So here's what I need you to do over the weekend. I'm not going to collect this, of course, but you know, karmically, it would be a great thing to do for you, your math karma. So now, let lambda equal 162/8, which is actually 81/4, so that equation 2 becomes 2y times 1 minus 81/4 equals 0. This is not 0. What does that imply about y?
It's 0.
Y must be 0. Go back to the constraint to get the x. You're going to get 2 new points. So use 3 to get 2 distinct x values. And we've got 4 points now. We have 4 points. And the 4 points are going to be 0 plus or minus 3. So 0, 3, 0, minus 3. And then you're going to make the 2 here that are going to be something 0, something else 0. Plug those into the objective function. So plug those into the f that I gave you, 81x squared plus y squared, which will actually be a pretty chill computation. It's not bad because half of it's 0. So plug sub into f of xy, largest value equals max, least val equals min. These are, I mean, we're like literally almost done. Like, probably in the time that I'm saying do this stuff, we could have done it. So, just a real quick thing, and then I'll end this. But when we have that multiplier, so the lambda that you get represents how much the output value will change if we slightly tweak the constraint. So this is stuff like used in business and stuff like, and I clearly know nothing about business or making money or anything. And if I ever tell you to do anything, or you think like, is he recommending I do this? Do the complete opposite. Right, Alexander? All right, friends. That's it for today. So next Wednesday, skill checks. There'll be 4 of them. And then next Monday, we're going to start integration. Brant, you're welcome to come anytime you want. Christian, my friend, would you
Of course.
get the, thank you.